In this video, we're talking about taking electrical measurements with oscilloscopes. Our oscilloscopes look like the figure on the left, and our oscilloscope probes look like the figure on the right. The display area of the oscilloscope plots a graph of the voltage measured by the probe versus time. Just for orientation's sake, the big draw of the oscilloscope is that we'll be able to plot the voltage that the probe measures versus time in this display area. So they're useful for measuring changing signals. Now, oscilloscopes are almost always used with the oscilloscope probes on the right. It's possible to screw BNC cables into these little terminals, and in fact, you can see an example of that here. We just used a BNC cable to hook the signal generator up to the oscilloscope. But BNC cables can corrupt your signals in really surprising ways unless you know what's going on. Oscilloscope probes will almost always measure things right. As a result, you should always use oscilloscope probes. Now, there's one exception to this rule in E80. When you're just hooking up the signal generator, like we showed over here, using a short BNC cable is okay, and often much more convenient than hooking up a pair of hooks to the end of your signal generator cable and clipping those to a BNC cable. The probe pictured here has an adjustment switch, and that's true of about half of the oscilloscope probes in our labs. The adjustment switch switches the probe between two modes called 1x and 10x, and you should almost always be using a 10x probe. So if you're using the adjustable probes, check that it's set to 10x mode. If you're using one of the gray probes, they're always set to 10x automatically. You also need to make sure that the oscilloscope is set to the same mode as your oscilloscope probe. So if you use a 10x probe, you can check on the oscilloscope whether the channel is set to 10x by pushing one of the channel buttons. If you're doing this direct BNC connection, then you need your channel set to 1x mode. Because people are going to be swapping those back and forth, you should always check your channel settings to make sure that they're correct. Now, the hook on the probe is where you pick up your signals, and you should attach that to your desired signal. This claw should be grounded. Now, over the next few slides, we're going to belabor that this claw is attached to earth ground, and so unlike the multimeter, you can't hook your oscilloscope probe ground anywhere in your circuit and have it still work. That has to be hooked to the same ground as everything else in your system. Now, I have two pet peeves about handling of oscilloscope probes. One is that students like to wrap wires around the tips of the oscilloscope probe, and that tends to bend the hooks, which makes them kind of unusable. It's much easier just to leave the spare wire that you would wrap around the tip in your breadboard, and then grab onto it with the probe. The second is related to this plastic piece on the end of the probe. It turns out it's possible to take this plastic piece, which I call the probe hat, off of the oscilloscope probe, and that's useful because there's a needle probe inside which can be used to get at voltages that are hard to reach with your hook. But sometimes people, after removing the probe hat, will lose it, and that drives me absolutely crazy. Don't lose your probe hat. And if you're not sure about what I'm talking about, just don't take it off at all. And then finally, whenever you're storing your probe, make sure its hat is reattached securely. The equivalent circuit model for an oscilloscope probe is drawn here in my sort of usual cubist art stylings. The equivalent circuit model is a pair of resistors which are attached between the hook and the claw connection of the oscilloscope probe. I'm deliberately not giving you the values for those resistors right now because measuring them or looking them up is part of your lab work. That said, you already know that an oscilloscope measures voltages, and from the multimeter voltage measurement video, we know that if an instrument designer wanted to reduce the loading of an oscilloscope that an oscilloscope presented to a circuit, they might make a particular decision about whether those resistors are big or small, and so think on that carefully. Now, you might find it weird that this model uses two resistors instead of one. Indeed, from the point of view of the circuit, which is living out at the end of the hook and at the end of the claw, those two resistors can just be combined in series. However, we include two different resistors in the model because they're in two physically different places. The first one is contained inside of the input channel of your oscilloscope, and the second is contained inside of your scope probe. This model also gives us a really convenient way to understand the difference between a 1x and a 10x scope probe, because the voltage that the oscilloscope reads is the voltage across the lower of these two resistors, the V-scope raw, that's annotated on this plot. Now, that V-scope raw is obviously going to depend a lot on this upper resistor, and in turn that upper resistor is what gets set when you switch the 1x and 10x switch on the outside of your probe. There's software inside of the oscilloscope which corrects V-scope raw, so it knows what that divider ratio is going to be and multiplies it back up so you get a correct voltage reading on your screen. And that's why it's so important that your oscilloscope is set to the same 1x, 10x setting as your probe is. But all of those details aside, remember that for the purposes of calculating loading on your circuit, you'll only really care about the series combination of these resistors, which look like just a single resistor connecting your hook down to your claw and earth ground. Now, the fact that the claw on the oscilloscope is attached to earth ground makes it a whole lot different than the multimeter that we've been looking at so far. It means that the oscilloscope claw needs to be really carefully placed into a circuit because earth ground is really insistent on its voltage level, and as a result, every earth ground in your circuit needs to be attached to the same point, or else you're going to get shorts in the circuit called ground faults. So I've drawn a circuit that this oscilloscope probe is connected to, and this connection probably wouldn't have a ground fault, but it also probably wouldn't measure exactly what a designer intended. Because you have the claw hooked to this node of the circuit, that node of the circuit is earth grounded, and so you would be measuring 0 volts across your resistor, because your instrument has effectively made this node ground, and it just happens to have a dangling voltage source hanging down here, which means that this bottom node would actually have a negative voltage if you were able to measure it with some sort of floating measurement. Now, usually in a schematic drawn like this, we'd expect the bottom node to be ground, so these results would be surprising. So if this VN source were not isolated, which is how it's currently drawn, but instead were referenced against earth ground like this, you would actually have a ground fault. Because here we have 2 different values of ground with a voltage source between them, and that would result in short circuit and lots of current flowing and some weird voltages in your circuit, and lots of dramatic red lights showing up on your instruments. So be careful to always hook your earth grounds to the same spot. In this case, the claw needs to be hooked up down to this bottom node, and if you really want to get the voltage difference across this resistor, you need to use 2 different oscilloscope probes and hook one hook on the left and one hook on the right. Now, it's easy to become drunk with power on the oscilloscope in the lab. It's a really wonderful and interactive tool, and you can put a lot of data on the screen in lab and pull it off quickly by using cursors and measure functions while you're prototyping. However, often students stop gathering this data after they've taken a screenshot of the oscilloscope, and that really limits the amount of useful post-processing that they can do. Sometimes they even forget to take a screenshot and they're left without data when they write a report. So please make sure to save your data, and make sure to save it as CSVs, and make sure to save it all the time, just because disk space is cheap and your lab time is very expensive, especially in the 80. And then finally, if you're comparing 2 sine waves on a Bode plot, sure, you can present a time domain plot that overlays them, but don't forget that Bode plots are really powerful tools for expressing the relationships between sine waves across frequency. So to summarize the main points of this video, oscilloscope probes have an equivalent circuit of a resistor going to ground. And there's a bunch of nuances about the inside of probes and the fact that that resistor is actually a divider, but the long and short is oscilloscopes are a resistor to ground. We also need to remember that oscilloscope probes are referenced to earth ground. They're not isolated measurements, which means that you need to be very careful when you're grounding them, or else you'll create accidental shorts in your circuit. When you're using oscilloscope probes, make sure you're using 10x mode, and also keep your scope channel set to 10x mode. And also be careful with the probes, don't damage them, and be sure to save your data.